Welcome back, everybody, to the last session. We were just giving one of our chairs a little more time to come online, but he doesn't seem to have made it. So we'll have to proceed without him. Hopefully, he'll join as we continue. So this is the final session of the day. We're talking about further research prospects, and we're going to conclude with the round table discussion. So chairs for this session are Martin Unwin, who's a principal GNSS engineer at SSTL. I see he's just joined, and that's Nazareno Pierdica. He's a professor at Sapienza University of Rome. Welcome, Mauro. And then when we get to the round table, we have Estelle Cardelac from the Institute of Space Sciences. She will be the chair for the round table. So over to the chairs.
So Mauro, are you online to introduce the first speakers?
Okay,
not,
yes,
okay, good.
I am here, okay. So thank you, Peter and Martin and Estelle, who are co-chairing this session. I think we can start, and then Estelle will take care of managing the questions. So we can start with the first presenter, that is Brandi Downs from Ohio State University. And the presentation is about Cygnus level 1 analysis for inundation. So Brandi, the floor is yours.
Okay, thank you very much. Okay, so I'm assuming everyone can hear me and see my screen. So
okay.
I'm Brandi
Yes,
Downs.
we can.
Okay, great. I'm Brandi Downs. I'm a PhD student at Ohio State University, and I'm working with the group shown here with these co-authors, and I'll discuss our work with Cygnus level 1 inundation analysis, as well as an ongoing collaboration with Nystar. So first, I'd like to thank my co-authors at JPL, at the Dartmouth Flood Observatory, and at University of Sogno in Benevento. So this work is being done as part of a NASA ROSES 2017 project titled Dynamic Mapping of Tropical Wetlands and Inundations with Cygnus, with Dr. Cinzia Zufata as our principal investigator. And the project focuses on understanding and characterizing the signal that's received by heterogeneous scenes that contain both water and vegetation. Some of our current and prior work is shown on this slide. So some of the work that we've done involves modeling the reflected signal, both as the sum of both incoherent and coherent components. We've looked at developing methods for coherence detection, including this entropy-based coherence detection developed at University of Sogno. And then we've looked at retrieving several different surface parameters, including wind vector and water depth. And in 2021, this project was augmented to include a flood applications component. So this component, again, is led by Cinzia Zufata at JPL, and the additional collaborators are Andrew O'Brien at Ohio State University and myself. And we are collaborating with the Dartmouth Flood Observatory, or DFO, that's at University of Colorado Boulder, and they act as a gateway to potential end users of the applications product. So our overall goal is to apply Cygnus-based inundation analysis and retrieval algorithms in support of the needs of the applications community, and explore the benefits of the Cygnus data for use by practitioners in decision-making. So to give an overview of the DFO, they are a not-for-profit that started in 1995, currently hosted at the Institute of Arctic and Alpine Research at University of Colorado Boulder. And some of their hydrological products include automated, near real-time, and optically derived flood inundation maps, such as the one shown on the right. These maps can be provided to relief agencies and emergency managers for operational use. The data sources include MODIS, Landsat, Sentinel-2, and Viirs. And of course, all of these being optical remote sensing based, one of the challenges is that these methods have difficulty observing inundation beneath clouds and vegetation. So this figure at the right is an MODIS-derived product generated at the DFO that shows surface water, and then MODIS is a 250-meter resolution product. So one of the case studies we're looking at currently is in South Sudan. South Sudan presents a challenging location for optical-based observations due to its extensive vegetation cover, which can be seen in the land cover map at right. So it's covered in savannas and grasslands primarily, and then the Nile flows through the center of it, but is mostly permanent wetlands. The surface water extent in South Sudan is highly variable, and we have the Al Sud wetlands in the center where the surface water extent can change on a daily basis. So flooding in the summer and fall of 2021 was characterized as the worst in decades, and it impacted over 700,000 people. And so in order to explore that, I wanted to look at the last 4 wet seasons and see what the Cygnus measurements show over South Sudan for those 4 wet seasons. So we started in August of 2018 because that's when the Cygnus V3.0 data was first available. And this animation that will show a moving 30-day window of Cygnus normalized reflectivity from August 2018 through August 2021. So we see, kind of expected high reflectivity along the Sud region until we get to the summer and fall of 2019, which becomes significantly greater in extent. And then if we continue on through the drier season, we come into the wet season of 2020. Again, the surface water extent is very much greater than that of 2019 or 2018. And then continuing through to 2021, we see again that the reflectivity shows a much higher extent for 2021. So it appears, at least from the Cygnus reflectivity, that the last 3 years have actually been seeing significant flooding. Next, we compare the Cygnus reflectivity with MODIS and Viirs for October of 2021. So on the right, we have a gridded reflectivity product data set from Cygnus, and then we have Viirs in the middle and MODIS on the left. And if we apply thresholds to Viirs and Cygnus, we can generate these water masks. And so we see that MODIS, as compared with Viirs, significantly underestimates the surface water extent for this month, while Cygnus looks like it could potentially overestimate, although some of this could be explained due to Viirs being visible in infrared and having greater difficulty seeing water beneath vegetation. So performing a more quantitative analysis and comparison between these data sets, as well as with Sentinel-1, is a study that is currently underway. Next, I'll talk about our collaboration with the NASA Isro Nystar mission. So the Cygnus science team is actively performing land calibration and validation for soil moisture and surface roughness. But of course, Cygnus is also producing these new terrestrial surface water observations that have applications for monitoring wetland extent and detecting dynamic inundations, as we've shown in the previous slides. And CalVal of wetlands is more complicated due to the lack of in situ and remote sensing data and the heterogeneous scenes. Meanwhile, a new joint NASA-ISRO SAR mission, Nystar, will make high-resolution global L-band observations every 12 days, and CalVal activities for its wetlands product are currently underway. So just to explore the complexity of wetland scenes, we show this land cover map over the Mississippi River. This shows a mix of both open water along the Mississippi River, woody wetlands shown in light blue, and then forest on the right and cropland on the left. And this image kind of conveys the complexity that a real wetland scenario presents as compared to a simple non-vegetated water body. So to give an overview of Nystar, it's an L and S band synthetic aperture radar mission that's due to launch in 2023. It will make high resolution observations with a 12-day repeat cycle, and it's tasked to produce wetlands products and map global inland and coastal wetlands every 12 days with at least 80% accuracy at a 1 hectare scale. So CalVal activities of the wetlands product are currently underway, and Nystar has allocated significant resources to the calibration and validation that could be leveraged by Cygnus and the GNSS-R community. So one of the CalVal sites for Nystar is Yucatan Lake, which is a small oxbow lake along the Mississippi River, located between Louisiana and Mississippi. And this is a lake that is around 50 square kilometers with 10 to 20 meter tall trees. And we see the last 10 or so years of inundation extent, or actually stage level, at the nearby Vicksburg, Mississippi gauge. And we can see very significant fluctuations, seasonal and annual, along this, from this gauge up to 10 meters in change. So some of the activities and available data that are associated with Yucatan Lake include Cygnus, RAW-IF, and DDMs. We have UAV-SAR data that one of the data sets can be shown here on the top. And then we have L-band ALOS-2 data. We also have some in situ sensors, including pressure transducers, a time-lapse camera, and river gauges on nearby Mississippi River. And then we have recently installed citizen science water level indicators. Here we see one of those time-lapse cameras on Yucatan Lake, or it's actually just southeast of Yucatan Lake. So here's the lake, and here's where the time-lapse camera is. Mississippi River flows, and then about 44 river kilometers north of that is the Vicksburg gauge. And so we show the time-lapse camera and the Vicksburg gauge and changes in both. Sorry, my computer has frozen. But what you can see is sorry, I'm gonna have to stop sharing just for a second and try to reshare. Okay, so hopefully the Vicksburg stage readings and the time-lapse camera are showing up on the screen again. So again, we can see the water level as it rises, and then as it lowers, and is shown as well in the gauge readings. Okay, there we go. So our group has also begun looking at Cygnus data at this CalVal site. So here we show results from our entropy-based coherence detector to observe the presence of water. So for entropy-based coherence, a low entropy is indicative of a coherent signal and water, and then high entropy indicates a dominantly incoherent signal, and it indicates land. So where we see low entropy, so these plots are actually inverted. So where we see low entropy is where it's higher, and this indicates flooded area during a wet season. And then here on the right, we see a dry season, and you see shorter periods of flooding or shorter areas of surface water. Here we compare the Cygnus RAW-IF signal in black with a Yamaguchi decomposition of UAV-SAR data. And so we see high entropy again over land, low entropy over surface water, which includes open water as well as inundated vegetation. Let's see. And so where we see open water, we get a higher level of surface scattering or single or odd scattering from the UAV-SAR data, and where we see inundated vegetation, we get a higher level of double bounce. So this shows a very good agreement between the L-band Cygnus signal and the L-band UAV-SAR signal. We've also used Cygnus to create maps of gridded signal to noise ratio over this area that show changes in seasonal inundation. So here we have a grid of over the full year of 2019. And here we show a grid just during the wet season of 2019. So this is kind of a 3-month period versus the dry season. And so we can, use these grids to look at seasonal changes in this area. And then recent modeling and analysis by our team is also being used to advance measurements of surface water. So for our citizen science component, we've partnered with Crowd Hydrology, which was started by Chris Lowry at University at Buffalo. And he has installed several crowdsourced river water gauges. And the way they work is basically just a meter stick in the water and this kind of picture that asks, what's the water height today? And it gives a phone number, and people can either text the height that they see, or on some of the gauges, they can actually take a picture and send in the photo. So one of the uses of this is that we were hoping to be able to see when an area is inundated and when it's not, because there's such a huge variation in surface water inundation in this area. And finally, the flood applications work presents a new and exciting opportunity to learn more about how Cygnus data can complement current operational flood products and benefit end users. And the collaboration with Nystar and leveraging of the Nystar CalVal activities presents a unique opportunity for Cygnus CalVal. So this could provide validation data that would be a key component for production of a GNSS-R wetlands and surface water extent product. And up until now, land validation data and activities have focused on soil moisture only. Thank you.
Thank you, Brandi. Very nice presentation and interesting results. Estelle, can you take care of questions, please?
Yes, sure. At the moment, there are no questions. I see we have 1 more minute. So maybe I can ask you about the detection, the coherence detection algorithm using the level 1 data, not the raw data samples. Mm-hmm. I'm not sure that I understood if it's just the reflectivity levels or if you apply, this is using raw data, right?
Are you talking about the entropy-based coherence detection, or are you talking about the earlier slides where we show reflectivity?
Well, I don't know. I only got the entropy based, but I understand the entropy algorithm uses raw data samples. So yes. I was wondering about level 1, the algorithm using level 1 data.
So currently, we are actually developing a comparison between these different coherence detection methods. So that's something that's underway. And but as far as a level 1 coherence detector, I know Mohammed Al-Khaldi has developed kind of a power ratio. But what we show here with the level 1 data is just the normalized reflectivity. So it's actually a combination of signal to noise ratio as well as the trailing edge and leading edge slopes. And that, it's just basic thresholds that are applied to those.
Thank you.
Sure.
There are no other questions in the question and answer box. And I think it's time for the next speaker. Thank you, Brandi.
Okay, thank you again. The next speaker is Eric Loria. He's from JPL, and the presentation is about the scattering and coherence modeling. So, Eric.
Hello,
please.
Can you hear me okay?
Yeah.
All right.
Can you share the screen?
Yeah, I'm looking for the correct one here. Okay.
Yeah, fine.
Sure. All right. Great. So I'll play this and then I'll take questions. Hello, everyone. My name is Eric Loria. I'm from the Jet Propulsion Laboratory. And today in this presentation, I will be talking about some of our recent work modeling GNSS-R coherent scattering in inland waters. To begin with some background and motivation, our work here aims to understand and characterize the GNSS-R signal in heterogeneous wetland and other inland water environments. The main goal is to examine how Cygnus and other future GNSS-R missions are able to produce products of dynamic wetland inundation extent, vegetation type and density, or other inland water products. So this is primarily achieved by a combination of theoretical modeling and validation, as well as observational efforts using Cygnus data. So this work presented here is being done as part of a NASA ROSES 2017 project called Dynamic Mapping of Tropical Wetlands and Inundations with Cygnus, with Cinzia as our PI. Here's a brief outline for the rest of the talk. First, I'll be talking about scattering models for coherent reflections in these heterogeneous scenes. Second, we'll examine some of the sources of variability that we observe in the coherently reflected power. And finally, we'll look at validation of the scattering model using Cygnus RAW-IF data. So first, we will look at an overview of the scattering models we use for the GNSS reflection in complex heterogeneous wetland areas. It is well known that the total DDM power can be written as the sum of two main components, the coherent and the non-coherent. The form of the diffuse component is well known and is given by the bistatic radar equation shown here. While some of our other recent modeling efforts have addressed the non-coherent component, the work presented today will mostly focus on the coherent component. Over these inland water areas, diffuse power may arise over wind-roughened surfaces. However, at low to moderate wind speeds, the coherent component is likely to dominate. In this slide, we show how we model the received coherent power from a reflection. The traditional method is to use equations based on image theory. However, that approach assumes an infinite scattering plane, which is not a safe assumption in practice for inland water scenes. By starting with the Kirchhoff diffraction integral and working our way through some math and a few approximations not shown here, we arrive at this equation for the coherent power. It is an integration across a scattering surface, as different areas may contribute different amounts of electric field and thus power to the total received signal. It can be observed that most of these terms in the equation are well known or well characterized. However, I have highlighted three significant unknowns in red. These are the surface roughness, vegetation attenuation, and the geometry of the scattering surface itself. The next few slides will briefly examine these three sources of variability in the received power. So the first source of variability in the reflected power we'll examine is the surface roughness. Surface roughness can play an extremely important role in determining the total reflected power. For most spaceborne reflection geometries, the coherent component will exist for surfaces with RMS surface height changes approximately fewer than 5 centimeters. The figure below shows an example of the power loss for several incidence angles with increasing RMS height. The signal is highly sensitive to this small-scale roughness effect, something which our team has exploited to look at wind vector and wave height retrievals in inland waters. The second main source of variability in the received power comes from vegetation. As the electromagnetic waves propagate through the vegetation, the signals are attenuated. For most crops and vegetation, the vegetation nadir optical depth is written as a function of the plant water content. It is common to use a linear relationship between the nadir optical depth and the PWC, along with an empirical constant determined by the wavelength, polarization, and the canopy type and structure. Finally, this is mapped into a signal attenuation for a two-way total reflection path with respect to the incidence angle, shown here at the bottom of the slide. The figure below shows signal attenuation for several incidence angles versus the plant water content. It can be seen that for the higher incidence angles, the path through a given canopy height is typically longer, and therefore the vegetation attenuation will be higher. The expected attenuation can cover a significant portion of the dynamic range of the Cygnus S and R values, which are approximately 0 to 24 dB, and can drastically reduce the signal power. Finally, the third main source of variability comes from the surface geometry itself. The phase values in the integral described earlier projected onto the surface form what are called the Fresnel Zones. Subsequent changes in phase of 180 degrees from the specular point define increasing Fresnel zones. An example for a Cygnus geometry at 50 degrees is shown here. it can be observed that the first Fresnel zone is an ellipse, and the additional Fresnel zones are rings of increasing diameter, but decreasing area. However, the area change from one Fresnel zone to the next is pretty small. Even and odd-numbered Fresnel zones are in phase opposition, meaning that alternating zones will add destructively. For simple scattering scenes, these Fresnel zones end up partially canceling each other, creating a variability in the peak received power. An example of this is shown below, where we take a circle scattering area of increasing size. So at the beginning here, on the bottom left, you see that there's very low SNR because there's very little scattering area. However, as you increase the scattering size, it approaches the size of the first Fresnel zone, it fills up, it gets to a peak power value, and then comes down as additional Fresnel zones are added in, at which point they're starting to add constructively and destructively, leading to an oscillation and significant variance in the received power for even small changes in the scatterer size. For complex scenes, we do not know ahead of time how the Fresnel zones will interact with the shape of a scatterer. The received power is then a function of both the scattering geometry and the surface itself. The figures to the right illustrate this complex variability. For each scene shown in black and white, the simulated coherent returns are generated. The specular point stays fixed, but the azimuth and incidence angles were changed. The plots on the right can be interpreted as the received SNR for a given azimuth and incidence angle pair, with 0-degree incidence at the center of the circle and 70-degree incidence at the edge. It can be seen that for the same surface, there can be a difference of 15 dB in the received power solely due to the observation geometry. In addition, no clear pattern of the reflection geometry in the SNR is visible. Over the past few slides, we have demonstrated that the three main sources of variability in the peak reflected power, such as the Fresnel zones and scatterer shape, the vegetation, and the surface roughness, will all contribute to determine the total received coherent power. For lower incidence angles, we expect the surface roughness loss to decrease, but any loss due to vegetation will increase. This is due to a longer path length through the vegetation. Conversely, for lower incidence angles, the roughness loss will increase and the vegetation attenuation will decrease. In general, we expect the transition in reflected power between a scene with surface water and a scene without to be large, but the power will be modulated by both the Fresnel zone behavior as well as the vegetation and roughness effects. We expect that in order to retrieve one parameter, the other two must be known. Unfortunately, it may be challenging to disentangle the three, making it difficult to measure the water extent or the vegetation content accurately using conventional inverse problem type approaches. It may be beneficial to try and use new approaches to these problems and to try and retrieve parameters such as methods based on machine learning or other approaches to reduce the dimensionality of the problem space. Now, for the last component of this talk, we'll look at a validation of the scattering model using the Cygnus raw IF data. So in order to best validate the scattering model we created, we chose to use the Cygnus raw IF data. The Cygnus raw IF mode is a special collection of raw samples for short periods of time that are stored at an intermediate frequency. So this mode is particularly useful for our study for several reasons. The first is that the coherent integration time can be increased from the nominal 1 second, which allows for the production of higher SNRs when coherent reflections are appearing. Second, there is no 0.5 to 1 seconds of incoherent DDM averaging. The along-track smearing of these measurements can then be minimized and determined by our selection of any incoherent DDM averaging that we want to do. And third, the access to the phase data allows for the accurate detection of the coherent power itself. For validation purposes, we were looking for something that best represented the simple water or no water scattering scene and a well-observed water body with a stable shape. We were also looking for targets surrounded by steep slopes or dry land to minimize scattering contributions from the land itself. Also, a target without vegetation eliminates another confounding variable. We eventually landed on Lake Ilopango in El Salvador and received several raw IF overpasses from the Cygnus project. The images below highlight the stable shape of the lake. For the model validation, we implemented the coherent scattering model into a modified version of the Cygnus end-to-end simulator. The SOC data provided the antenna gains, the EIRP, and the receiver and transmitter geometry. We used the PECL data as a water mask to determine the scattering surface topology. 2 specular tracks that cross a lake were selected for the matchup. These tracks occurred at times with low winds, and we selected a coherent integration time of 5 milliseconds. And the next slide shows comparisons of the measured and simulated signal-to-noise ratio. In the top left figure, we show the specular track as it crosses the lake from the northwest to the southeast on day 229 of 2019. In the bottom left, we see the track from day 234 of the same year, passing over the lake from southwest to northeast. In both cases on the right, we can see that the simulated and measured waveforms match closely, even where we see the Fresnel zone diffraction patterns at the edge of the lake. So finally, we end with some conclusions and next steps. There are 3 main sources of variability in the received coherent power: the surface roughness, the vegetation, and the Fresnel zone effects. For heterogeneous scattering scenes such as those we see in the wetlands and other inland water areas, integration over the surface must be performed. We proposed an equation for these types of scattering scenes. The close match between the measurements and the simulation confirms the accuracy of the scattering model while using the Cygnus raw IF data. The edge diffraction effects due to the Fresnel zones were visible in both the simulated and measured power waveforms. With many different variables affecting the received signal in inland water scenes, it may be that techniques such as machine learning would be required to help reduce the dimensionality of the retrieval algorithms and the problems that we're trying to solve. Our current modeling efforts include higher order interactions between the vegetation, surface water, and wind, and to continue to develop retrieval algorithms for inundation mapping and vegetation type and density in wetlands. So thank you very much for watching my presentation, and I'd be happy to take any questions. Thank you.
Thank you very much, Eric. A very rigorous approach to the problem. Estelle, can you manage the questions?
Yes, at the moment there is no questions, just a complaint that the PPT was not in full resolution and was not readable. But yeah. I do have, in fact, 3 questions. So I see we have 5 minutes. Maybe I can ask some of my questions while waiting for other questions in the question and answer box.
Sure.
So the first question, the first question is about the last slide in your second block when you mentioned that that it would be difficult to distinguish all these effects in standard retrieval algorithms. I assume that what you mean is if we only use the power or the reflectivity, right? Because some other observables. So these conclusions came from an exercise on the reflectivity, on the received power. So, for instance, this statement would not include any approach that uses the phase, for instance, right?
That's correct. So I think, yeah, so there's quite a few variables that are introduced into the problem, right? And in order to solve for those variables, I think you need more sources of information. So yeah, if you only use the reflectivity or the signal to noise ratio or some component of the power, then I don't think you'll have enough information to constrain those problems. However, if you do introduce other ancillary data sources or perhaps, yeah, the phase, I think you would be able to come up with enough inputs to produce an output there. So I do think you're correct there that you would have an ability to try to tease out some of the information in these complex scenes.
Thank you. I see there is a question now. Anania Ray asked, will Cygnus plan to start giving coherent channel data?
I think so. I guess I'm not exactly sure what they mean by coherent channel data, but yeah, sorry, I'm not entirely sure how to interpret that. Perhaps maybe they mean like what you can do with the standard raw IF data downlinks. So that's the only time you can get, say, the complex data is these short bursts of the raw sample collections, at which point you can do your own coherence processing. Otherwise, the L1 data, yeah, you have whatever is produced normally by and distributed by the SOC. Yeah, okay, the complex DDMs. Yeah, so I don't know of any plans from the Cygnus project to produce complex DDMs, probably due to the downlink capacity that they have. However, yeah, so you'd have to move towards the Cygnus raw IF collections, of which they are starting to ramp up more and more over targeted areas, as selected by the Cygnus science team. And at that point, you can process these raw data samples and produce the complex DDM outputs.
Thank you. I see we have 2 more minutes, so I might ask another question. The last block of your presentation was the validation of the model, but I understand that you selected a lake or an area that besides the water, there were no vegetation or little vegetation. So I assume that what you have validated are the effects of the water itself. So whether the modeling reacts to the presence of water, and probably also the topography, the slopes of the terrain, but not the vegetation component of the model, right? Or maybe
yeah.
I misunderstood.
No, that's correct. So yeah, we're also working on the vegetation component. Part of the selection of this lake, as a first order look, was because it does represent a much more simple scene. So if we wanted to have an excellent validation over an area with vegetation, then I think we would need to have much more information about the vegetation itself. And when you start looking for truth data to use as inputs to the model and to compare with the measured data, then you start running into problems because we don't really have a great set of truth data. And so that's one of the things that we're looking forward to with this Nystar cross calibration and validation effort, is that we'll be able to utilize the resources of that project for their wetlands project for us to use as well. So I think we'll be able to get much better sets of calibration and validation data from that.
Thank you, Eric. I think now it's time for the next speaker. Thank you very much.
All right, thank you.
Thank you, Eric. And now the end of the workshop is approaching, so it's time to make some conclusion. And in fact, the next presentation will be given by Martin Unwin, also on behalf of the whole HydroGNSS team. And it is a summary of meeting and HydroGNSS prospects. Please, Martin.
Okay, can you hear me?
Yeah.
All right. I'll just set a few things up. And what I thought we'd do now is that as we're coming towards the end of the workshop, I just have a quick recap of what we've covered through the 2 days. It's been a busy day, too busy 2 days. So the first day was really focused on the mission itself, HydroGNSS. We had opening introduction from ESA about their new Scout program and about HydroGNSS, and we had UK Space Agency and their actions following the COP climate mission, what they're trying to achieve with their activities, and an introduction from SSTL about HydroGNSS and how it fits in with the other satellites that SSTL has been producing. And we then went on to an introduction to HydroGNSS itself, talking about the mission and the implementation, introduction to the team and our experiences with the Scout program. And then the science team of HydroGNSS gave a presentation on the different level 2 products that we're producing, aiming to produce for HydroGNSS. So the soil moisture product from Sapienza, the freeze-thaw state product from Finnish Meteorological Institute, and inundation from IEC and forest biomass from IFAC, and the secondary product, the ocean wind speed and ice extent from NOC. And we then heard more of the mission details, the design of the instruments, systems, measurements and calibration. And DOT1 as a precursor and demonstrator for HydroGNSS, and the payload data ground segment and end-to-end simulator. Complementary activities with SMOS and biomass. Unfortunately, that presentation had to be cancelled. We hope to hear more about that another time. But then Clara Chu gave a presentation on the soil moisture experience from Cygnus mission, which was very interesting, and it gave a challenge to HydroGNSS that not to force the data to a grid. There's plenty of experience from Cygnus. And then we heard some research activities. So there's a digital elevation model on board the satellite that's keeping the signal in the center of a delayed Doppler map. And then we heard more about the background of GPS Galileo signals and how their relevance for the reflectometry. And then we heard more about the detailed modeling within the Savers simulator that's being used by the HydroGNSS team, and then from IEC, some more details on using the raw IF data sets and what can be discovered from looking at that helps towards the mission. Then we heard from Maurizio about a new metrics that could be used for measuring the coherence, the entropy that's based on eigenvalues that can give a clearer measure of how coherent the signal is. And then we heard from the activities in CESPIO, and in particular, some of the work on biomass and the desert. Very fascinating that reflections are being picked up from subsurface fossilized rivers, and the aerodynamic roughness of particles, which affects aerosols. That's being measured by Cygnus as well. Then we went on to users. So we heard some fascinating talks from the ESA CCI, their program for collating measurements from satellites towards essential climate variables. And they talked about soil moisture, biomass, and fire disturbance is an interesting one that we should think about for HydroGNSS. Sort of faster version of biomass that finds the fire damage, and the permafrost. And then we heard from the Copernicus Climate Change Services and ECV services at the ECMWF, and the climate data storage, and also that the soil moisture is currently one of the things that's being tracked, but the surface inundation and freeze-thaw may one day become new ECVs, possibly, which is fascinating. Then we heard from from Wolfgang Wagner on the challenges and the use and validation of satellite soil moisture data. And he identified some of the challenges and the opportunities that we have with the HydroGNSS satellite. And then we heard from Milad in GFZ about some of the work they've been doing on hydrology using GNSS signals, and also a fascinating new application, which is measuring the rainfall out at sea using measurements from GNSS reflectometry due to the salinity changes and the roughness changes that's observed from reflections. And then we heard some of the parallel experiences from other missions. So Adriano gave us a lot of experience from his long work at UPC, and some of the experience in terms of some of the non-linear effects we may need to look out for, what the opportunities that L1 and L5 offer, and what was achieved with FSSCAT. And then we heard from Konying about the progress, the rapid progress that's been made with the Chinese GNSS reflectometry. It was only launched in July last year, but it's on the operational satellite mission, Fengyun 3E, and they're getting good results from the reflectometry over land. And then we heard from Phil Jail's Inspire, which is, he was presenting a commercial approach of CubeSats, constellation of CubeSats, which are taking all sorts of measurements of, including soil moisture, and they're able to track multiple constellations, have many measurements, and they're providing a service which is combined with SMAP and Cygnus data as well. And the combination of these things is giving very good results. Hugo Carino presented the experience from Cygnus, particularly the high altitude ones over the Andes, the Rockies and Tibet Plateau, which was very valuable experience towards HydroGNSS, showing about how the freeze-thaw can be measured through the seasons. And then we heard from Brandi Downs about the flood activities, how Cygnus might be able to contribute towards that, and the calibration activities with Nystar, and from Eric Loria about some of the complexities which offer opportunities but also challenges with the really high resolution stuff with the Fresnel zone that gives you a resolution of up to 500, as good as 500 meters, but it introduces these ripples as well, and it's all affected by the roughness and the geometry, and unpicking those different complex terms is going to be a challenge, but it does offer opportunities, and they may be relevant for HydroGNSS as well. And we've not been able to cover everything in the 2 days. There are other activities going on. The Taiwan Triton mission, the Chinese Bufeng 1A and B, and the ESA Pretty mission are things that are happening. Spaceborne missions, and there's numerous ground and airborne campaigns, and there's also plenty of other research and modeling, calibration, data applications. But I think what we've managed to gather together is a lot of material in 2 days that has been very relevant towards HydroGNSS. And so I gathered some statistics yesterday, and I think they're already out of date. So we have, this is the number of presentations, 35 presentations. I think the number of registrants to this workshop has been over 300. I think we don't get 300 logging in at once, such as the world of an online event, but we've been getting well over 100 a lot of the time of people logged in. The number of organizations is hard to estimate because sometimes people give them different names, but we think it's about 140. And we think it's about 30 different countries have participated in this workshop, and that's 6 continents. So it's only missing someone from the Antarctic. Next time we'll do better. So we've done very well with the number of people in this workshop and the attendees. So I think just a few comments on prospects. for HydroGNSS. So following the kickoff in October 2021, the Scout 2 HydroGNSS mission has a status all systems go. So we passed the system requirements review in January 2022. The next review we're working hard towards is the preliminary design review, and we are already negotiating for a launch for 2024. There is a prospect for a second satellite. We are working hard on seeing if we can make the stars align to make this happen. If it happens, then it will be launched on the same launcher into the same orbit, and that would give us an opportunity to double the measurement coverage and reduce the revisit time. And it would be also an important step towards a constellation, improve resilience and improve calibration. So, but even with a single satellite, HydroGNSS is a low-cost, high-value science mission. It's targeting hydrological variables which are vital for climate observation. As you all have seen from this workshop, we're getting good engagement from researchers and users, and a large number of registrants to this workshop. The next workshop will be planned, according to our plans, it will happen sometime prior to launch in 2024. So watch this space. We will announce when we have our workshop, so it's going to be some time yet. But before then, there's a lot of meetings with GNSS-R content, not least, there's going to be a GNSS reflectometry workshop probably next year. I think we're already discussing where that's going to be taking place, so watch this space for that. The first meeting that we think we're going to be attending in reasonable numbers is the ESA Living Planet Symposium Bonn in Germany in May 2022. So we're hoping that some of the people from HydroGNSS will be in there in person. And of course, I need to plug the GFZ workshop, which is Milad presented, is I can't remember what time it was, but whether it's May or June, but we will make sure that that's highlighted. And so maybe people will be attending that as well. And now I think we are going to hand over to Jean-Pascal Lejault from ESA first to give a few concluding comments, and then Phil Brownnett from SSTL. And then we will have a roundtable discussion at the end with a number of questions and a number of panel members to address these questions. So at this point, I shall hand over to Jean-Pascal, who is the ESA Scout Project Manager. So over to you, Jean-Pascal.
Thank you, Martin. So I'll give a summary in a different fashion from what you did, Martin. So I don't have slides, but so a summary from the ESA perspective. And I mean, as in a nutshell, for me, this was a very inspiring workshop with very positive vibes. And I'm quite impressed by the excellent expertise and know-how which was involved during this workshop. And I'm also extremely pleased with interest which was expressed, as you also spotted, Martin, expressed during the whole workshop, and the high expectations I perceived from all. I would like to express my, I would like to say many thanks to SSTL for organizing and holding this science workshop. You did very well organized. Also, many thanks to all participants for the very valuable and complementary talks, which were casting light from different angles. And for me, that was quite valuable information. Now, from the quality of the talks, the large attendance and the open discussions held, I'm also very much impressed and happy about the strong interest shown in HydroGNSS and the very high expectations from all participants. I can feel a vibrant interest in HydroGNSS. I also feel that HydroGNSS is much awaited, and for me it's quite rewarding and inspiring, and it makes me even prouder to be the project manager in ESA for HydroGNSS. So a big thank you all for these very positive signals, very well received. And if you allow me a GNSS-R related joke, I mean, I received these signals both as direct signals and reflected signals. And thank you for that. So now if I go into a bit more of details, as I said, HydroGNSS, I feel, is very much expected. It's clear, it's recognized already as an asset, potential asset in the making. It will provide very valuable data to scientists and services, and for instance, CCI, C3S, Spire. It will complement other sources of data. It will also potentially serve as a gap filler in the L-band soil moisture measurements, which also demonstrates the value of a short-term development cycle, which is typical for the SCOUT framework. And it will also support decision makers, especially to fight against climate change, which is undoubtedly one of the top issues that mankind is facing. Another point is that though there are multiple stakeholders and teams involved on HydroGNSS, it's clear to me that we are all sharing the same objectives and we work together as a great team, bringing both relevant and complementing expertise. And for me, that's a key achievement already. And I think we can all be proud of being part of this endeavor. So this for me is already a very good and first success. I can also see many other opportunities for collaboration with other stakeholders who are not already involved in HydroGNSS, for instance, to merge more sources of data to improve science return and data accuracy. I'm very confident that HydroGNSS will be a success in multiple ways. I mean, first, it will provide valuable data to scientists and decision makers. It will also, from visa perspective, I think it's important because it will demonstrate the relevance of the SCOUT framework for future opportunities. And in any case, it's my personal commitment and drive to make HydroGNSS a success for these two reasons. On the SCOUT framework, which I would like to highlight, I think it's confirmed that the SCOUT framework makes sense and is very much welcomed by the community as a valid and relevant complement to other frameworks. So I think that's clear. I also think that HydroGNSS, as the first SCOUT mission selected for implementation, is completely fulfilling the requirements and expectations at the inception of a SCOUT program, if not going beyond. And this is also very promising. It's very promising for HydroGNSS. It's also very promising for the SCOUT framework. So now, what are the next steps? I see two aspects for HydroGNSS specifically. I mean, I can see a lot of energy, ideas, suggestions, proposals, synergies, and we need to build on these to get the best out of that for the sake of HydroGNSS and as a way to transform its potential into reality for the benefit of us all. On this topic, ESA is fully committed to serve the user and scientific community and decision makers to the maximum extent, no doubt about that. And in particular, and building on what Martin said, it's important to ensure that a second recurring HydroGNSS satellite is supported and approved at the next ESA conference at ministerial level, which will take place in November this year. And the next step for SCOUT in general, I would like to promote a bit the SCOUT framework. I'm not only the project manager for HydroGNSS, but also for CubeMap, and which is another SCOUT mission. Don't miss the second SCOUT call, which will be discussed at CIMIN 22 in November, and spread the word about the new SCOUT framework in ESA and its benefit, as you can already witness. And please share the positive experience on HydroGNSS to stimulate other SCOUT missions. So we keep in touch, of course. And again, a big thank you to SSTL for the organization and program and to all participants for this excellent and inspiring workshop. Thank you very much.
All right.
Yeah, thanks, Jean-Pascal, and thanks, Martin, as well. So Phil Brownnett is on the MD at SSTL, and I think it just remains for me to maybe just to reiterate what you've said, Jean-Pascal. Thank all of the attendees for joining us over the last 2 days, to hear and discuss the HydroGNSS mission. A great and many thanks to the presenters for your time and support for the event and some very interesting discussions and topics. And of course, many thanks to the organizers who've helped shape and run this conference smoothly. So yes, again, many thanks to all. As you said, Martin, we've had a large number of participants, up to over 200, almost 300. I think you said at the end now registered and attended. So that shows the popularity and maybe the importance of the topic on GNSS reflectometry, and of course the interest in the new HydroGNSS mission, which we say has been made possible by the foresight of the ESA Scout program, and I think that's important. The initiative from ESA is very exciting. It heralds a new and practical way of applying the new space small satellite approach to address science, that would normally maybe be here now, approached by larger satellites with many years of schedule. So yeah, SSTL and our science partners have already been working closely and effectively with ESA. We've made good progress since the kickoff, and we are focused and we are committed as well to delivering on time for a launch in 2024. So the team will take great sort of support from this workshop and carry on to ensure that we deliver on the prospects and the mission as has been outlined today. The HydroGNSS does make use of obviously GNSS reflectometry, which is in effect, as we know, a radar without the needs for a transmitter, and a great Earth observation technology for small satellites. It's new measurements pushing the boundaries of what we've been achieved before. But as you mentioned, Jean-Pascal, the demand for the higher temporal resolution can really come with multiple satellites. So there is a lot of interest in the considered option for a second HydroGNSS satellite. We can double the measurements, halve the revisit times, and boost the science value for a relatively small investment. Monitoring needs a path, a sustainable route for a constellation of such small satellites. Whether that's institutionally or commercially funded, or more probably as we look to the future, a combination of both through commercial partnerships. So I think to conclude this conference, I believe we're holding a roundtable discussion next that will be discussing further some of the topical questions in light of the workshop that we've just held. So once again to everyone, thanks for your attendance, and I can hand back to the session chair.
Thank you very much, Phil and Jean-Pascal.